Okay, just one more. Let's find the absolute max and absolute min values of this function on this interval. It is a closed interval, and so we know for sure that the function will take on some largest possible value and smallest possible value on this interval. What we don't know for sure is whether those max and min values will be determined using the derivative or by simply plugging in the endpoints. Because we can't tell ahead of time, we're going to pit them all against each other and see which one wins. Okay, let's get to playing. So what we're doing here is finding the derivative first. So find the critical numbers. That'll be found by getting f prime. This is quotient rule, of course. So we've got 2x from the derivative of the top times the normal version of the bottom, x squared plus 4, minus the derivative of the bottom, that's again 2x, times x squared minus 4, over the square of the bottom, x squared plus 4 squared. Okay, well, let me collect this a little bit. I've got 2x cubed plus 8x minus 2x cubed. Oh, look at that. That's so nice. And then plus 2x times 4 is 8x. And then that's over x squared plus 4 squared. Okay, and just one more rewriting of that because these are just begging to be crossed out. 8x plus 8x is 16x over x squared plus 4 squared. Now, remember, I'm finding critical numbers of this, which are points where the derivative is either equal to 0 or fails to exist. I know this seems like we're never going to find one where it fails to exist, but this is another one where the derivative will not fail to exist. The reason it doesn't fail to exist, is that the bottom of this is never going to be 0. So critical numbers will be found purely based on the top. So this equals 0 means that really we're just wondering about when 16x equals 0. That, of course, only happens when x equals 0. Now stop and ask yourself, does this occur in the interval that we're talking about? The interval we're talking about is right here, from -4 to +4. The answer is yes, it does. Now, if I were asking you to classify this critical number as a local minimum or local maximum, you would be putting it into a number line, getting those values out, and then saying, oh, it went from increasing to decreasing, and that's fine. But here, because the goal is to get the absolute max and absolute min values on this interval, it's going to be sufficient to just take this number, don't even bother identifying whether it's a local max or local min, just throw it in the function and then compare it to the values at the endpoints. And that will give you your competitors. Okay, so let me see. So plug in and compare to values at endpoints. Here we are going to evaluate, let's see, 1, the critical number, f of 0. Yes, it is f of 0. We want the values of the function. This is going to be 0 squared minus 4 over 0 squared plus 4. That is -4 over +4 for a value of -1. Okay, now we will plug in endpoints. Endpoint of +4, f of 4 is going to be equal to 4 squared minus 4 over 4 squared plus 4. 4 squared is 16, minus 4 is 12. 4 squared is 16, plus 4 is 20. So this is 3/5. So far, this seems like it's going to be a maximum. Let's see, though. Now, the endpoint of -4, you may be able to see what's going to happen here, because look, x is squared every time it appears. So we're going to have negative 4 squared minus 4 over negative 4 squared plus 4. Well, wait a minute. Because I'm squaring everything, it doesn't make any difference that I put in negative 4 versus positive 4. This is going to end up being the very same 3/5 that it was before. So here I have my competitors. I have this one, and this one. So the absolute maximum value of the function on this interval is going to be 3/5, because that's achieved not even just once, but twice. And the absolute minimum is actually the one that I found by using the relative minimum. The absolute minimum value is -1. Cool, huh? I always think so.